Alright, in this video we're going to talk about how we can calculate delta H for a reaction using a few other methods. So we've talked about calorimetry using experimental technique to determine Q values and then delta H values. Today we're going to look at non-experimental methods. Hess's law is one of those methods that allows us to use delta H values from other reactions in order to calculate the delta H of a given reaction. And this is based on the idea that enthalpy is a state function. So in the diagram that we see here, we have multiple pathways between initial reactants A and final products B. If we're trying to find this delta H1 for our direct pathway, we could use delta H values that we know of for other reactions, such as A going to C and then C going to B, or A going to D, D going to E, and then E going to B. Despite the fact that there are different pathways that we can use, we can employ the idea of state functions to determine that the pathway is irrelevant to our delta H calculation, and that regardless of which pathway we picked, we would get the same value for our delta H1. This shows an example of that using a real reaction. So if we start down here with our carbon, our H2 gas, and our O2 gas, we have two different pathways that we can go that would produce two different products. The pathway on the left goes to carbon plus 2 water molecules. The pathway on the right goes to carbon dioxide and 2 H2 molecules. You'll notice that the delta H values are different for these two different reactions. But we can use both of these delta H values in order to determine the direct pathway between carbon and water molecules to create CO2 and H2. Alright, and that's this value here. So this employs the idea of Hess's law. Hess's law says that if a reaction is carried out in a series of steps, delta H for the overall reaction will be equal to the sum of the steps. So even if we're looking at finding the delta H for a one-step process like we have here, we can still break it down into multiple steps to calculate delta H. Here's another example using the same kind of idea but broken down a little differently. If we're starting with methane plus O2 in a combustion reaction to create CO2 and H2O, and we're looking for the delta H for this direct pathway for the combustion reaction, we could break it down into two steps. Methane and O2 creating carbon monoxide and water and O2, and then second step combining some of those into the further products of CO2 and water. Since we broke it into two steps, we would need to know the delta H of the first step and the delta H of the second step. By doing that, we can then add the two steps together to get our overall value for delta H for the reaction that we're interested in. Since delta H is a state function, it only matters where we start and where we end. It only matters that we're starting with our methane and our O2 and we want to go to CO2 and water. It doesn't matter how many steps in the middle to get there. Alright, here's our mathematical way of saying the same idea. Hess's law of heat summation. The delta H for the reaction is equal to all the delta H values for every step along the process. So we can break one overall reaction down into multiple steps when we know the delta H for each of those steps in order to find the overall delta H. Many delta H values for common and well-known reactions already exist, and we can look these up on tables. So we don't actually have to do the experiment to find what they are. Once we know the delta H values for the steps and we want to put them together, there's a couple of different things we can do to manipulate the delta H values. So if I start with the example of H2 plus O2 goes to H2O, and I have a delta H value given for this reaction, the negative 571 kilojoules. If I then reverse the reaction, so I flip it around, so my products become the reactants, all right, so we're flipping this over here, and reactants become products. When I flip it around, I get this reaction here, and notice what happens to delta H. My first reaction was a negative 571. When I flip it around, it becomes positive 571. The numerical value stays the same, but only the sign switches. So if it is negative in one direction, it becomes positive in the opposite direction. Alright, so when we're comparing reactions, sometimes we might have to flip them around to get them to add up in the direction that we're interested in. The other thing that we can look at is the magnitude, which has to do with the coefficients in front of our compounds. So our original reaction, we had 2 in front of the H2, 2 in front of the water, and 1 in front of the O2. But if we divide the reaction by 2, or multiply by 1/2, if you prefer, this reduces the coefficients to 1 for H2 and 1 for H2O, and then 1/2 for O2. And notice what that does to the delta H value. Since I took 1/2 of the coefficients for the whole reaction, I'm going to take 1/2 of the delta H value, and that's where I get this. Alright, so whatever we do to the reaction itself, we're going to do the same thing to delta H. If I flip the reaction, I'm going to flip the sign. If I multiply by a cofactor, I'm going to do that same thing to the delta H value. For this process, it is okay to have fractions for your coefficients. Because as we saw when we were calculating delta H for thermochemical equations, coefficients are important and coefficients matter for that delta H value. So it's perfectly fine to have fractions. Alright, so we're going to walk through this example and then we're going to look at a couple of others. But you want to get a feel for how we can use Hess's law in order to find delta H. So in this question, we're trying to find the delta H for our reaction here. We have 2 sulfur plus 3 O2 gives us 2 SO3. So we want to know the delta H. We're going to use the two equations given below in order to find the delta H. So this is going to be similar to a puzzle. We need to manipulate these two equations that were given to make it look like this one up here that we want. So the first thing I want to look at is placement. I have sulfur on the left side as a reactant. So if I look for sulfur in my two equations here, here's my sulfur. The other equation doesn't have it. So I need the sulfur, the S, to be on the reactant side, the left side, and it is in this equation. Alright, so I'm using that one. Now my O2 is going to be a little trickier because it is in both equations on opposite sides. So we're going to come back to O2 in a minute. Let's look for SO3. SO3 is again only in one of the equations. It's down here in the second equation. But I need SO3 to be on the right side, the product side, and right now it's on the left side of this one. So that means I need to flip this second equation around. Alright, so I'm going to rewrite it as 2SO2 plus O2 makes 2SO3 gas. So all I did was flip it around, and remember when we do that, the delta H flips signs, so now this is negative 198. Alright, so I'm going to cross out this guy. We're not using him, we're using the flipped version. Alright, so now I have my SO3 on the correct side, I have my sulfur on the correct side, and now I have an 1O2, in the first equation, 1 O2 in the second equation, which when I add them together would give me 2 O2s, but obviously I need 3 of them. So now that I have everything in the right place, my next thing is to look at how many I have. I have 1 S, but I need 2. I have 2 O2s, but I need 3. And I have 2 SO3s, which is exactly what I need. Since this is what I want, I'm not going to bother with this last equation again. But I am going to go back up here and multiply this equation by 2, so that I have 2 S's and 2 O2s. When I add that to the second equation will give me 3 O2s. Alright, and remember, if we multiply by a cofactor, we do the same thing to the delta H. Alright, so now if I look what I have 2S plus 3 O2s. Notice what happens to my 2 SO2s. They're going to cancel each other out because they're on opposite sides of the arrow. And then I have my 2 SO3s. So that's exactly the equation I wanted. Now I want to look at what my delta H is going to be. So I have negative 297 times 2, which gives me negative 594. I'm going to add to that the negative 198 to give me negative 792 kilojoules for my delta H value. Alright, so by manipulating those two equations, we can find out the delta H for the third one. And this shows you exactly what we did again. We multiplied the first equation by 2 because we needed twice as many sulfurs, we needed more oxygens. And then we flipped the second equation so that we had the SO3 on the correct side. We did the same manipulations to delta H, so multiplied the first one by 2, multiplied the second one by negative 1, or flipped the sign, and then we added everything together to give us our answer. Alright, so being proficient at these just takes some practice. We're going to do a couple more examples just so you get a feel of this. There's also some practice worksheets that go over this if you want to practice more. Alright, so in this one, we have 2W plus 2O2 gives us 2WO2. That's what we're looking for. We have these two equations down here to try to help us out. So we're going to do the same thing. I have W on the left, so here it is in my second equation. I need WO2 on the right side, and it's up here. So that means I gotta flip this one around. Alright, to get my WO2 on the correct side. Alright, so I'm gonna write that down here. 2WO3 goes to 2WO2 plus O2. And then our delta H is gonna flip signs. Alright, so I'm gonna cross out this one. We're not working with him anymore because we got him flipped around. Alright, so now I have 2W, that's what I need. Over here, my 3O2, I'm going to be able to cancel out one of those because I have an O2 over here, so that leaves me with 2. That's what I want. And then I have 2WO2, and notice my WO3s are going to cancel. Alright, so 2W plus only 2 of the O2s left. Gives me 2WO2, and then of course over here we do the same thing for our delta H's. Since I flipped the first equation and flipped the sign, I'm going to add it to the other equation, so I have negative 1180 kilojoules. Okay, alright, let's try one more example. PCl5 goes to PCl3 and Cl2. We have two equations we can work with in order to get this one. Alright, so let's start with PCl5 on the left. Alright, it's here, already on the correct side. PCl3 over here, already on the correct side. And then our Cl2, we have Cl2 in two places. Alright, so let's just work with what we have. We don't want to flip anything because we have PCl5 on the correct side, PCl3 is where it needs to be. So let's just add together what we have and then we'll see what's left. So our P4s are going to cancel out. They're on opposite sides of the arrow. So I'm left with PCl5. And over here I have 6 Cl2s, but I have 10 over here. So all of these are going to cancel out. I'm going to be left with 4. Alright, so I have 4 PCl3 and then 4 of the Cl2s. Alright, so all we've done is add the two values together so far. So when I add the two values together, I get 999 kilojoules. But notice it doesn't exactly look like my equation I want yet. I still have coefficients of 4 in front of everything, but up here I only have coefficients of 1. So we're going to multiply the whole thing, including delta H, by 1/4. So when we do that, I'm down to 1 PCl5 and 1 PCl3 and 1 Cl2. And look what happens to delta H. I'm also going to divide it by 4, which ends up being pretty close to 250 for the delta H value. Okay? So it could be multiple steps, could only be one step. Make sure you have everything on the correct side first, then you can address the coefficients. Make sure things that you don't want get canceled out. Alright, so we talked about calorimetry in a previous video. We talked about using combustion reactions to find delta H. We talked about Hess's law now, using other equations to find delta H. And the last one we're going to look at for calculating delta H comes from heats of formation values. These are values you can look up on a table in order to calculate delta H, and so we'll look at that. And then the last thing we're going to look at is estimating delta H based on energy required to break and form bonds. Alright, so before we get into heats of formation, we need to look at some nomenclature. When we see delta H, that is talking about the change in enthalpy. And we can calculate this for any reaction or process using products minus reactants. So state function. Only matters where you start and where you end. It's essentially final minus initial. If we see delta H with the little 0 next to it, that little 0 indicates standard state. It indicates that this delta H was calculated under standard state conditions. Alright, we're going to talk about what standard state conditions are in a second, but just be able to recognize the little circle means standard state conditions. Adding to the little circle, this last one, we also have an F. So standard state conditions, this is change in enthalpy of formation. So the little F means formation, and we're going to get to what that means as well. Alright, so we can calculate delta H for any reaction. We can also find delta H at standard state conditions, or we can find standard state conditions for heat of formation. Alright, so standard state conditions. This means in my reaction, when I'm calculating delta H, all of the gases in my reaction are pure, they're not mixtures, and they have a pressure of 1 atmosphere. Alright, liquids and solids are also pure. They're not mixtures, they're not alloys, and they are stable at 1 atmosphere again, okay, because we're at 1 atmosphere pressure. any solutions that are in my equation. So these are the ones that would be called aqueous. Solutions are stable and have a concentration of 1 molar. And then typically we see standard state values given at 25 degrees Celsius. Although it's not required to be at 25 degrees Celsius, that's just the most common that you're going to see tables of. Sometimes you can find standard state delta H at other temperatures, but not always. Alright, and then standard heat of formation. So if we have the little F on there as well, that indicates a particular type of reaction used to calculate delta H. A heat of formation means taking the elemental states of the atoms that make up a compound on the reactant side and adding them up to make 1 mole of the compound. Alright, so for example, if I want to make nitric acid heat of formation reaction, nitric acid has hydrogen, nitrogen, and oxygen. So I'm going to take those elements in their standard states, okay, at 1 atmosphere, 25 degrees Celsius. What state are they in? So H2, N2, and O2, if you remember, are diatomic, which means 2 atoms together to make the molecule, and they are all in the gas state. So I would need H2 gas, N2 gas, and O2 gas to make HNO3. Now I also need to balance it. For the product side, I can only have a coefficient of 1. So this is for making 1 mole. So I can't change the coefficient on the product side. I can change the coefficients on the reactant side to balance this. So I would need 1/2 of H2 to give me 1, 1/2 of N2 to give me 1, and 3/2 of O2 to give me 3. Alright, so that would be a heat of formation reaction equation for nitric acid. If I then had a delta H value that went with this reaction, that would be called an enthalpy of formation or a heat of formation value. Alright, so a couple rules with the heat of formation equations. You're only making 1 mole of the compound, so your coefficient on the product side must be 1. You are using elements on the reactant side. Everything on the reactant side must be an element from the periodic table, so no compounds. Alright, so carbon plus O2 can be used to make CO2. Carbon is a solid at our 25 degrees Celsius and 1 atmosphere. O2 is diatomic and is a gas. And it's already balanced. 1 carbon, 2 oxygens to make CO2. So this would be the heat of formation equation. If we look at this second one, sodium, solid, perfectly fine, that's an element, plus Cl2 gas, perfectly fine, chlorine is diatomic and it's a gas. But on the product side, we have a 2 in front of NaCl. We cannot have that. So if we wanted to make a heat of formation reaction for NaCl, we would have to write Na plus 1/2 Cl2 gas creates 1 mole of NaCl solid. Alright, so we have to have the right coefficients. Other example down here, MgO solid plus H2O liquid to give us MgOH2. This is not a heat of formation because both of these are compounds. MgO and H2O are compounds. We can only have elements on the left side. So if I wanted to write a heat of formation for MgOH2, I would start with magnesium solid plus O2 gas plus H2 gas. Alright, and that would give me my MgOH2. And this one would already be balanced. Alright, so only elements on the left side. Only 1 mole of product on the right side. Rule number 2, standard state. Everything must be in their standard state, meaning what state are they in at 1 atmosphere of pressure and 25 degrees Celsius? Are they solids? Are they liquids? Are they gases? Alright, if you look on the periodic table, there's only 2 liquids at those standard conditions, bromine and mercury. The right side is going to be mostly gases, so all your noble gases are gases. H2, N2, O2, Cl2 are all gases. Alright, once you move further left, you're getting into the solids. Everything else is a solid. Alright? So even if we have something elemental like H2, if it's in the liquid state, that's not under standard state conditions. So H2 liquid cannot be included in a heat of formation. It has to be H2 gas. Now a couple of things have multiple forms at standard state. So for example, oxygen can be O2 or O3. Both of those exist under standard state conditions. O2 is used because O2 is the most common. Carbon also has multiple forms. We have graphite, we have diamond, Buckminster fullerene. All of those would exist under standard state conditions. We use carbon as graphite because it is the most common. Alright, the heat of formation of elements are defined as 0. So if I wanted to know what the heat of formation of H2 is, it's just 0, because the only way to make H2 is to start with H2. It doesn't get any simpler than that. Since elements are the basic building blocks, we can't break it down any further to have the same properties, so delta H of heat of formation value for any element is 0. This table shows you some values for heat of formation for several different atoms or compounds or ions that exist. So notice all the zeros correspond to elemental forms. Once you start creating ions, we see changes in these delta H values. When you start creating compounds and adding atoms together, we see changes to the delta H values. Okay? You can find tables of these values in your book and online for just about any compound or ion that you're interested in. Alright, so we're going to start with writing our heat of formation reactions, and then we'll look at using the values to calculate delta H. So if I want to know heat of formation for CCl4, well, that has carbon in it, which is solid, and it has chlorine in it, which is a diatomic gas. I want to make 1 mole of CCl4. So in order to balance, I need 1 carbon, but I need 2 of the Cl2s. Alright, so C6H6, same idea. I'm going to start with carbon, and I'm going to use H2, elemental form, to make C6H6, and then balancing means I need 6 of the carbons and 3 of the H2s. Alright, so remember, we're only making 1 mole. We can't have a coefficient other than 1 on the product side. We're only using elements on the reactant side in their standard state, and then we can change the coefficients on the left side to balance it. Alright, calculating delta H from these heats of formation, we're going to follow the same idea we had before of products minus reactants, and we're going to apply this to a whole reaction. So we're going to add up all of the delta H values for products and subtract from that all of the delta H values for the reactants. So this is our summation. Right, so that's summation. N is our coefficient. So N is a coefficient of delta H of formation values at standard conditions for all of my products, minus Okay, here's my summation again. M is my coefficients for all of my delta H values, standard state conditions for heats of formation, for reactants. Alright, so we're still doing products minus reactants. We're using the coefficients to multiply by our values. We're adding up all the products, and we're going to subtract from that all the reactants. Alright, so here's an example. If I want to know delta H for my C3H8 plus 5O2 gives me 3CO2 plus 4H2O. So my combustion reaction, I'm going to look up heat of formation values for all of my components of my equation. So I have 3 times the CO2, 4 times the H2O, those are my products. Then I'm going to subtract 1 times the C3H8 and 5 times the O2. So products minus reactants. Then I'm going to look on my table and fill in these values. So my negative 393.5 was for CO2, negative 285.8 is for the water, negative 103.6 is for the propane, and then notice O2 is 0. Why is it 0? That's elemental. Okay, all the elemental ones have 0 for delta H. Then we just complete our math and we get our delta H value. Okay, and notice it is negative, which means exothermic. All combustion reactions are going to be exothermic. Alright, let's try another one. Alright, so to calculate delta H, we're going to do products minus reactants. So 2 times negative 150.2 plus 2 times negative 285.8. All of those are my products. Then I'm going to subtract 2 times 245.9 plus, notice O2 is not listed here. Why is that? Because we know what O2 is. It is 0. Alright, now we just have to complete our math. So I will point out something to make sure that you are aware of. We are subtracting everything on the reactant side, so make sure to distribute your negative appropriately. So if we look over here first, we have our negative values for both of these, so we're going to get a very large negative number first. And I get negative 872 here. And then, of course, this is going to be a negative number on this side. Negative 491.8. But I have a minus. So minus a negative makes it positive. So negative number plus a positive number is going to give me negative 380.2. And this is kilojoules. Alright, delta H is just kilojoules. We've multiplied the coefficient, so this will be the number of moles times the value. So that's going to cross out our moles when we look at units. Alright, let's try one more. Products minus reactants. So we have 4 times negative 1,279. That's all of our products, minus negative 1,640 plus 6 times negative 242. Alright, so remember to distribute your negative appropriately when you do your calculation. And for this one, I get negative 2,024 kilojoules. Alright, so that's pretty straightforward. Just make sure you pay attention to your math and use your calculator appropriately with your negative signs. Alright, last idea about heat of formation. You may have noticed on those tables and when we were doing our calculations, majority of the heat of formation values are negative. Alright, so when we put bonds together, when we put atoms together to create bonds, usually energy is lost. Okay, so most of the time when we're forming new bonds, it's an exothermic process. So we get a negative delta H value. Now, that doesn't mean every single one of them is negative. There are some compounds that have positive heat of formation values. But typically a positive heat of formation value indicates an unstable compound, indicates instability in that compound, which can mean that that compound doesn't exist for very long before it decomposes into its elements again, or decomposes into something else. Sometimes that decomposition has a near zero rate, so those compounds can still exist. So this is an example of one of those. So NO2, of course, is a compound that does exist. It does have an odd number of electrons, so it's what we call a radical. And it has a positive heat of formation value, indicating it's not all that stable. So it is likely to break down into an O2 or to react with something else because it has an odd number of electrons. So we have a positive heat of formation value indicating some level of instability. But NO2 still exists. So NO2 is still something we can isolate and we can see. It just means its rate of decomposition is not very quick.